Good morning, champ. Time to take things up a level. Last time we looked at partial derivatives, how one function changes when each variable moves separately. But what if we have multiple outputs, each depending on multiple inputs? We need one unified object that captures all those partial derivatives at once. And that's the Jacobian matrix. Think of it as the ultimate snapshot of how a multivariable function nudges space locally. It's the best linear approximation of your function near a point, showing how tiny input changes produce tiny output changes. Let's define it properly. Suppose f maps from r to the power of n to r to the power of m. In other words, it takes n inputs and produces m outputs. Write f of x1 through xn equals the vector bracket. f1 of x1 through xn, f2 of x1 through xn, and so on up to fm. The Jacobian matrix of F is the m by n matrix whose entry in row I and column j is the partial derivative of Fi with respect to xj. Rows correspond to output components. Columns correspond to input variables. Geometrically, if you make a tiny input step, delta x, the corresponding output change is approximately j minus f times delta x. The Jacobian acts like a transformation matrix. It turns a small input displacement into a small output displacement. It's how the function behaves locally when you zoom way in. Let's see it in action. Take f of x and y equals bracket x squared y, comma, sine of x plus y cubed, bracket. Compute the partial derivatives. The Jacobian is the 2 by 2 matrix. First row, 2xy and x squared. Second row, cosine x and 3y squared. At the point 1, 2, this becomes bracket 4, 1, cosine of 1, 12, bracket. That's our local linear approximation. If you nudge x and y a little, say delta x and delta y, the change in f is roughly bracket 4 delta x plus 1 delta y, comma, cosine of 1 delta x plus 12 delta y, bracket. Now for a geometric classic, polar to Cartesian coordinates, define t of r and theta equals bracket r cosine theta, comma, r sine theta, bracket. Its Jacobian matrix is bracket cosine theta, negative r sine theta, r cosine theta, bracket. The determinant is r times cosine squared theta plus r times sine squared theta, which simplifies to just r. That single number r is the local area scale factor. Tiny rectangles in r theta space become curved patches in xy space with area multiplied by r. That's why in double integrals, we always multiply by r when switching to polar coordinates. So, what does all this mean? The Jacobian tells us how a function stretches, squashes, or rotates space at a point. The rows show the gradients of each output component. The columns show how each input variable influences the outputs. The determinant tells us how much local area or volume changes, and whether orientation flips or stays the same. Quick recap. 1. The Jacobian matrix collects all partial derivatives into one clean package. 2. It acts as the best local linear approximation of a nonlinear map. 3. The determinant measures local scaling. 0 means flattening. Positive means preserving orientation. Negative means flipping it. 4. The Jacobian is the backbone of both the chain rule and the change of variables formula in multivariable calculus. So, the Jacobian matrix doesn't just tell us how functions change, it tells us how space itself changes.